Okay, today is May 30th, 2011. We're going to do lesson 7.6, but before we start that lesson, I'm going to take out question 9 from the quiz. So everybody just take out your quiz, look at number 9. I think only maybe 2 people in the class got all four marks for this. The question says to evaluate, and your final answer should be in fraction form. So the question says 4 to the power of negative 2 plus 3 to the power of 0 minus 2 to the power of negative 3. Since they want me to keep this in fraction form, the best way to probably go about this is to not use a calculator. Unless you have a calculator that puts things into fractions, this will become very difficult. So, first thing I'm going to evaluate, 4 to the power of negative 2, I'm going to change it to a positive power. So it's going to become 1 over 4 to the power of 2. 3 to the power of 0 is just 1. And subtracted by, again, I'm going to turn 2 to the power of negative 3 into a positive power. So it becomes 1 over 2 to the power of 3. Now that I've done that, I'm going to evaluate the other 2 powers. 1 over 4 to the power of 2 is 1 over 16 plus, I'm going to keep this as a whole number. And finally, 1 over 2 to the power of 3 is 2 times 2 is 4, times 2 again is 8. So 1 over 8. Many of you may have got this far. Congratulations. This is where you guys ran into trouble. Grade 4. I think I was tutoring a kid in this last weekend. Grade 4. When you add fractions, you need to have a common denominator. That means you have to change all of these to a common denominator. So 16 works great. With 8, I just have to multiply by 2, and 1 becomes 16 over 16. So I get 1 over 16 plus 16 over 16 minus 2 over 16. From there, my answer is going to be over 16. I just have to evaluate the tops of the fractions. So 1 plus 16 is 17. 17 minus 2 is 15. 15 over 16 is your final answer. Please, for this unit, go over your fraction rules. You'll definitely need to know how to use them. Okay, so we moved on to lesson 7.6. Again, you guys are on text page 425, Blue Notebook 354. We're going over growth rate today. So I've given you a formula. You need to remember this formula here. It is very important for today's stuff. These are the definitions of all the variables in the formula. So the first one, P at n, which is here, is the final amount. So usually what we're trying to find in most questions. P at O is talking about initial amount. The reason they use P is because we're usually dealing with populations when we're doing growth rate. So P at O would be like an original population of a town or a city. R is the rate of growth. So they will let us know how much a city is growing by percentage-wise. If it's a percentage, we'll have to change it into a decimal. And finally, N is the number of periods. So how many periods of growth are occurring when we're trying to solve our final number. So that sounds like a lot. We're going to try to put together in a question. So our example number 2 out of your textbook, we're going to go right to that. I'm going to read the question. There are 5,000 yeast cells in a culture. The number of cells grow at a rate of 25% a day. The function that models growth of yeast cells is, and they've given us a formula that is essentially the same as the one above. They just use different letters. 1 plus R to D. Where N is the number of yeast cells, so we need to take note of this. Anytime they change the variables in a question, we need to take note. So N equals number of yeast cells. D is days after the culture is started. And N at O is the initial population, which is pretty much the same as our P at O. But we'll write it down. Initial pop, we'll call it. Population. Okay? Oh, sorry, and R is growth rate, which we already know. How many cells will there be in 1 week? That's very important to the question. It's the last line. They almost just throw it in there. What we're going to do first is we're going to get all of the variables we have, and we're going to put number values for them. So our initial population, which was our N at O, N at O, initial population, how many cells were in the culture did they tell us? 5,000. So our N at O is 5,000. Our growth rate is what? Okay, 25%. Now, I will put it in as 25 for R. I have to change this percentage to a decimal. So what does it become as a decimal? 0.25. Very good, Lewis. And it says, sorry, and our D is talking about the number of periods because it grows at a rate of 25% a day. How many days are we measuring this culture over? How do we know that? Said 1 week. Very good. Oh, I'm glad you guys got that so easily. Good. So it's over the course of 7 days because they refer to it as a week, but our periods are measured in days. So we're changing it from 1 week to 7 days. Okay? So the exponent is going to be 7. So all this takes now is we just need to plug those values into our formula. So I have a value. Let's just quickly look. We have an initial value, a growth rate, and we have the number of days. We're going to be looking for the population at the end of a week. So in other words, we're looking for our N at D. So N D is equal to initial value of 5,000 multiplied by 1 plus 0.25 to the power of 7. I'm going to slowly go through this. 5,000, 1 plus 0.25 is 1.25 to the power of 7. Yeah, you simply just follow BEDMAS to solve this. You want me to bring? All right, we have the calculator up. 1.25 to the power of 7 is the exact number Lewis was telling us. I'm just going to put it to 3 decimal places. Instead of having to write the entire number out, just keep your answer from before in the calculator. It's going to help you become much more accurate when we do this unit. So instead of rewriting that whole number, I just have to hit multiply by, take the answer from above, 5,000. And the population after 7 days is 23,841. Obviously it goes into decimals, but we're talking about the number of cells, so I'm not looking at 0.85 of a cell. We need an entire cell, so it's an approximation if you guys remember. It's approximately 23,841. Thanks for your confirmation, Tom. Okay, since that was apparently easy enough, let's go to example 3. We're going to read it out loud. Many of the questions in this unit are going to be problem-solving questions when we deal with growth rate. So, according to the U.S. Census Bureau World Populations Clock, the number of people in the world in 1950 was 2.5 billion. The population has grown at a rate of approximately 1.7% a year since then. Create an algebraic model to predict the population in the future. So, first thing I'm going to do is I'm going to rewrite my formula. Population now is equal to the initial population multiplied by 1 plus the growth rate to the power of the number of periods. Since we're in the year 1950, okay, that's going to be our initial population, 1950. So our initial population in 1950 was 2.5 billion, also known as they've also told us that our growth rate is 1.7%, which is also, we're going to write it to decimal, That's not a happy face. That's supposed to be an arrow. 0.017. And it is per year. What's very important, guys, if you're going to figure out the number of periods, you need to know what the growth rate is at. If it's per year, per 10 years, every month, because that's going to change the number of periods in our growth rate. So in the question, they've asked us to create an algebraic model. We have that. What I would like to do now is, according to this model, we're going to try to find out what they predicted the population of the world to be right now. So what that means is, I have an initial population for 1950, okay? And we have a growth rate. I do not have the number of periods. If we're trying to find the population for now, what year are we in? 2011. How many cycles or how many periods have passed since 1950 to 2011? Good. So our N is going to be equal to 61. P at O is 2.5 billion. I'm just going to write the whole number out. And our growth rate R is 0.017. So now that I have all those numbers, let's see if their prediction of population growth in 1950 was accurate. Our formula was, yes? Sure. Second? Okay, so our formula is P at N is equal to initial population, 1 plus growth rate over number of periods. Our initial population is 2.5 billion. That is a lot. Our growth rate, 0.017, and the number of periods is 61. It's a very large exponent. Okay? So, I'm going to deal with brackets first. Remember, we have to follow BEDMAS. 1.017 to the power of 61. So let's put that in. 1.017 to the power, where is it? There it is, of 61 equals. Didn't turn out to be a very large number. Because we had a small growth rate. It was only a growth rate of 1.7%. So, 2.5 billion multiplied by 2.796. 1, 2, 1, 2, 3, 1, 2, 3. Make sure you put the number in properly. It's going to be hard to read. But according to that growth rate model, there's going to be 6,990,659,305 people in the world. Does anyone know what our population is right now? I think it's almost around 7 billion. So this is roughly a pretty accurate model that they gave us. We should go check this out. Okay, so we discovered after extensive research that the world's population right now is 7 billion. So 2011, that's most of the research you guys tend to do. Okay, so 7 billion is today's research. Sorry, not today's research, today's population. We're on the year 2011. So what we're going to find out, I actually want to know what the growth rate was from year 1950. Remember, our population then was 2.5 billion. Okay? And we have to figure out how many periods that was. So all that means is we're trying to find the growth rate per year. That means I just have to subtract 2011 from 1950. That's going to give us 61 periods, just like we had in our last question. So we're going to set up our formula. P at N equals PO times 1 plus the growth rate, power of the number of periods. Now, P at N, we actually already have that. P at N is 7 billion. So 7, 1, 2, 3, 4, 5, 6, 7, 8, 9 is equal to 2.5. Our initial population is 2500. working with very large numbers here, times 1 plus our growth rate we don't know. We're trying to find the growth rate between 1950 and 2011, but we do know there were 61 periods, okay? So the first thing I'm going to do is my whole goal right now is to isolate R. I'm trying to isolate that variable there. So this says 2.5 billion times this. So I'm going to move the 2.5 billion to the other side. In order to do that, what do I have to do? Anyone know? Divide both sides by 2.5 billion. Okay? So I'm going to divide both sides by 2.5 bill. I'm not writing that whole number out again. Okay? So we'll put that in the calculator. Technically, a fast way to do this would just be go 70 divided by 25, but I'll write it all out so you guys can see it. 1, 2, 3. 1, 2, 3. 1, 2, 3. Divided by 2, 5. 1, 2. 1, 2, 3. 1, 2, 3. Thank goodness we have a calculator we can see everything. That makes sense. So 7 billion divided by 2.5 billion is 2.8. So 2.8 is now equal to 1 plus R to the power of 61. Now, because this is in brackets, technically our next outside step is to the power of 61. I need to get rid of that power of 61. Does anyone know what the opposite of the power of 61 is? We went over this. 7.4 radicals. What is the opposite of the square root? Squared. Okay? So if I had something squared, let's say we had the number 4 squared, how would I do the opposite of that squared? I'd put the square root, so that's a root with a number 2 here. So if I have 4, let's say do 61, what would the opposite of that 61 be? Not the square root, but the 61st root of a number. Okay? So what I need to do is I need to find the 61st root of both sides of this equation. So I find the 61st root of this side and the 61st root of this side. Don't know what happened there. Okay, so when I said we have to find the 61st root, luckily what that means on the right side is we're just getting rid of the power of 61. So I'm going to be left with 1 plus R. But on the other side, I have to find the 61st root of 2.1. So if you guys remember, I would put in the number of 61, second function. No, that's square root. Okay, if your calculator doesn't have an x and then square root, another way you can find a square root is you put the base number in to the power of 1 divided by that number. That's the same as finding the 61st root. 1.017. Oh, that's exactly right. Okay, so I still have to isolate for R, so I bring 1 to the other side. I have 1.017, subtract 1. It turns out the growth rate was 0.017, which as a percentage is 1.7%. That is exactly what the book had predicted. That's amazing. I can't believe they knew that. Yeah. 1.7. Okay, that's how you do everything. You guys are geniuses. Do questions number 1 to 4 on page 423.